Swayam Prabha. Digital India. Educated India.
Welcome back to another session of blockchain technology and applications. In the last few sessions, we have learned a lot about Bitcoin consensus mechanism, but we haven't seen the details of transactions and how the transactions are validated by the different participants in the blockchain, and we also haven't seen how the blocks are validated. So, today we will talk about the Bitcoin blockchain mechanics. So, today's talk is entirely taken from the lectures and the book by Professor Arvind Narayanan of Princeton University, and it is a very interesting book. And if you are interested in learning all about Bitcoin blockchain and other alternative cryptocurrencies, then this is a very good book. I would recommend that to you, but we will be taking only selected parts of the book that is necessary for you to understand the basic mechanics of the Bitcoin blockchain. So, the consensus that we have seen allows us to have an append only ledger of transactions, and the consensus is decentralized. It is a distributed algorithm, but we overcome the impossibility results in the presence of adversaries or in the presence of malicious users, because we are using a probabilistic guarantee and eventual consistency. Also, we are using incentive mechanism, and the incentive mechanism has two purposes. One is why would I go and do the validation of your transaction? So, that is solved by giving incentives. The other problem, as we discussed, is that there might be malicious adversaries as participants, because this is a sort of pseudo anonymous network and it is very easy to enter the network. So, therefore, we use a mechanism for incentivizing the users to behave according to rules. So, one thing that you must note here is that Bitcoin blockchain is basically a blockchain for cryptocurrency creation and cryptocurrency transactions. So, if you have a blockchain, and we will see many blockchains that do not have a native cryptocurrency, and if they do not have native cryptocurrency, such incentive mechanism would not be available to us, and there we have to worry about other ways to solve the problem of validating transactions, validating blocks, and also creating the blocks that does not make the blockchain go in all possible directions and keep the consensus branch most longest branch, and therefore, make the blockchain integrity intact. So, what we mean by Bitcoin mechanics? Bitcoin mechanics mostly is about how transactions are done, what are the data structures that are used for denoting a transaction, and what are their purposes, why we need those kind of entries in the blockchain transaction structure, and also how people, the miners or other members of the other participants validate the transactions, and also we will look at the blocks and block validation. So, first let us look at the Bitcoin transactions. So, first thing one would think, having been used to the accounts based ledger, is that one might consider an account based transaction. And an account based transaction will look like this, that suppose I have a transaction that creates 25 coins, and I say that who it goes to, and this is asserted by the miners who create these 25 coins. But then let us say Alice transfers 17 coins to Bob and digitally sign the transaction, and then Bob transactions transacts 8 coins to Carol and signed by Bob, and then 5 coins are given by Carol back to Alice. Now, how many coins now Alice possess? So, there are 25 coins in the beginning which Alice got. She gave 17 to Bob, so she had 8, and then the next transaction does not involve her, but then the transaction after that gives 5 coins to her. So, she had 8 and now she has 5 more. So, she has 13. But in order to know that Alice now has 13, we have to go back to the very first transaction and work our way down in order to see where Alice got a positive inflow and where she got a outflow. And then we can also consider these as if these are the blocks, right. So, now let us say at this point Alice wants to transfer 15 coins to David. So, all the participants need to check the validity of this, and in order to check the validity they may have to go back to the first transaction where Alice had 25, then they find that next transaction Alice gives 17. So, she has 8, then next one she does it does not involve her, and the next one she gets 5. So, she has 13. So, she cannot give 15 coins to Alice. So, it is an invalid transaction. So, in order to decide that, we have to go through all the transactions that happened before, and if you consider each of these transactions as a block, we are basically going all the way to the genesis block to find out whether a transaction is valid. Now, this is going to be very difficult. Now, as we saw in our prototype blockchain that we actually discussed and given exercise on that, in that we were caching this balance information. So, every time we validate a transaction, we update the balance, and that is also possible to do, but that requires lot of more work for every participant, because every participant needs to validate these transactions. So, therefore, if they have to cache all this information, then they have to do a lot of work. And then there are few other complications, because sometimes the blockchain will diverge a little bit and then they converge back to the main consensus chain. So, therefore, those things becomes a little bit non-deterministic. So, that is not a very good solution to do. In our example that was left to you as exercise, there we were only one party that was running the entire program. It was not replicated all over the places. So, there was no non-determinism involved, but when you have thousands of participants involved and each of them are independently doing all this validation of transactions and also keeping track of the balances, there would be some inconsistency creeping in, and therefore, there could be some problem. So, therefore, this is not what Bitcoin does. So, what Bitcoin does is actually a transaction based ledger. So, they only keep track of transactions, not the account balances. So, the first transaction, for example, this is a genesis transaction, and what is happening is that there is no input to this transaction, but the output says that give 25 coins to Alice. Now, at this point, the next transaction only Alice can use. Now, what Alice has to do now is that she has to refer to the transaction that gave her the 25 coins. So, transactions are numbered. So, these are transaction IDs. So, she refers to the transaction ID 1, and then in this case there is only one output. So, the outputs are and inputs are basically can be thought of as arrays. So, she refers to the first entry of the output of transaction 1. So, this means I am inputting from transaction 1, and only way I can input something from the transaction 1 is from the outputs of the transaction. So, the output number 0. So, there was only one output here. So, output number 0 is 25 coins going to Alice. So, and then she says that my output has 2 entries. So, this is the entry number 0 and this is the entry number 1, where in the entry number 0 I give 17 to Bob and give 8 to myself to a different address. Remember the change address concept. So, Alice creates a change address which is different from her original address, and then she gives that money to herself, because otherwise there was a replay attack that we discussed before. So, now the next time there is a transaction. So, in this case Bob is making the transaction. So, Bob refers to transaction number 2 and entry number 0 in the outputs of the transaction number 2, which basically gave him 17 coins. So, out of these 17 coins he gives 8 to Carol and then gives to one of his change addresses 7 coins. So, therefore, now Bob has given Carol 8 and himself back 7. Now, in this one Alice again wants to make a transaction. Now, she has transaction, she got money in transaction 2, she cannot use transaction 1 anymore, because transaction 1 output has been spent. So, transaction 2 is the only a transaction where she got money. So, from herself only, but she got money there. So, she refers to the entry number 1 of the outputs of transaction 2. So, that is 2 indexed with 1, and there she gives 6 to David and then to her change address. So, this is the way Bitcoin does this. Transaction keeps track of the transactions, and note that in this case if we want to see whether this transaction is valid, all we need to do is to look at the transaction she refers to as a source transaction. So, her source transaction is this, and we see that in that source transaction in the output number 1 she got 8. So, that is all we need to check. So, now you see that we do not have to go all the way back to all the transactions. We also have to check whether Alice has used this transaction 2 indexed 1 anywhere between this transaction and this transaction, that also has to be checked. So, therefore, we have to only check a fraction of the transactions and not all the transactions all the way up to the Genesis transaction. So, that is the actually the Genesis, it is not called the Genesis transaction, it is called the coin based transaction. So, coin based transaction are transactions in which we create some coins, and those transactions do not require any inputs. Coins are created in those transactions. So, those are called coin based transactions. I was calling it intentionally Genesis transactions, but it is not really a Genesis transaction. Genesis block is a concept, not Genesis transaction, and Genesis block means the first block of the blockchain in which the blockchain started. So, we will talk about that later. But what we also do is that we create hash pointers to these different transactions, so that we can easily trace back when somebody refers to a transaction, we can quickly refer back to the transaction that we are interested in. Now, other thing we can do with this mechanism is that suppose I have multiple change addresses on many transactions. I got different number of coins into, or same number of coins, it does not matter. I got some coins on multiple change addresses, but it is very difficult for me to keep track of all those change addresses and how much I have in all those. So, time to time I may want to merge those change addresses, the contents of those change addresses into a single address. So, that is what is called a merging, and that is what we can do using like 2 input transactions. So, one from here and one from here. So, you see that the Bob can consolidate. So, here Bob got 17 in this transaction and Bob got 2 in this transaction. So, he should ideally have 19. So, he actually can create that by putting in a transaction where he refers to transaction number 1 output 0 and transaction number 2 output 1, and then he says that give 19 to me. Remember, the coins in the input transactions, these are called the input transactions to this transaction, and this is an output of this transaction. So, this is an input of the this transaction is an input of this transaction, and this is the output. So, output can be also multiple and input can be also multiple, and that is what we are seeing here. So, now we can also do joint payments, that is, if I do not have enough coins myself, and but I and a friend together decide that we will be using our coins together to buy something, we are allowed to do that. So, the joint transaction looks like this. So, let us say I have 2 transactions here, Carol has 6, Bob has 2, and they together decide to give 8 to David. So, they can put in a joint transaction, but remember that they have to both sign this transaction, because Bob or Carol themselves by themselves do not have the right to spend both of these outputs, right. So, they have to do a joint signing, and we will see how that works in a little bit. Now, in reality, so we gave you the schematics of what the transactions look like, but in reality this is what happens. This is the structure of a transaction, and if you actually go into like some real browser, this bitcoin.info for example, and then you can browse transactions and you will see things like this. So, what the transaction in the transaction structure, what we have are the following. So, we have metadata. So, this is the metadata, this is the data about the transaction. These are the inputs. So, you see that the input is an array. So, this array is denoted by this and finished by this, and then output is also an array. In this case in this particular transaction there is only one output, and I see there are two inputs, right. So, in the metadata what we have is the hash of the transaction, and then we have the version. This is the Bitcoin version. This says how many inputs are there. So, this is the input size, this is the output size. So, this is 2 and 1. There is something called lock time, and we will discuss very soon what lock time means. So, for now we can ignore it, except the fact that lock time 0 means this transaction can be done immediately. So, that is what lock time 0 means, the size of the transaction. And then in the input we have the hash of the transaction, that is the input, and N0 here means that this is the 0th output of the transaction, and then there is a signature. Now, how this signature is done, will defer that discussion for later, little bit later, but this is kind of like a signature, you can for now assume. Similarly, the second output also has the transaction hash for the previous second previous transaction, and then this is the 0th output of the transaction, and here is the sort of the signature. In the output you say what is the value of the value that you are sending, and this basically says the address of the person whose account is getting the funding, getting the money. Now, here you see that there is a lot of things, not only just account number. The account number is basically somewhere here, but the rest of it seems like a sort of like an assembly program, and we will see what that is in a little bit. So, that is what the transaction structure looks like. So, you get some idea about what this looks like. Now, let us look at this metadata and other inputs and outputs in a little bit detail. So, as I said that the metadata part has hash of the transaction, the version number, the size of the input array, the size of the output array, the lock time 0 means it is an immediate transaction, and the size of the transaction, and there may be some other data that might be there. So, that is a metadata. So, all of you know metadata means that it is a data about the data, right. So, this is the data about the transaction. So, this is what kind of says a housekeeping information, and this is the transaction hash, and lock time gives you when the transaction becomes valid. 0 means it becomes valid immediately. The input looks like this. So, you have the previous output transactions hash here. So, and then this is the index of the output of the transaction, and here is the signature, and we will see what that means. This is actually a public key, and this is a script that we will understand in a little bit. So, the output also has the value of the output, how many coins are going, and here it says who is going to be credited for that amount. And now, as we said that this kind of looks strange, but we will very soon understand what it means, and this part of that is actually a hash value, it is the account number, but we will understand very soon. So, Bitcoin scripts is what those things are. So, those mysterious things that you saw, like what says script sig, and in the output it says script pub key, and in the input it says script sig. these are actually what we call Bitcoin scripts. So, Bitcoin script is actually kind of like an assembly program, except that assembly programs are meant for real hardware machines, but in this case this script language actually has an idealized machine on which it is supposed to be executed, and this is a stack based machine on which this is executed. So, let us see how that works. So, first of all, like any assembly code, it has opcodes. So, it has opdup, for example, is an opcode which says that duplicate something that is on top of a stack. So, we have a stack based model of computation. So, data is pushed onto the stack, and then at that point if we get this instruction opdup, then we create a duplication of the top of the stack on top, right. So, if there is x on the top of the stack at the time I encountered this instruction, then I will write another x on top of it. Op hash basically hashes the whatever is on the top of the stack, right. So, and it basically does a 2 layer hashing. First it does SHA-256 and then it does a 160 bit hash. The output is a 160 bit hash. And here is some data we saw. In this case we said that this was actually a hash value, but it could be any data. And then this says op equal verify op check sig. So, op equal verify verifies that the top 2 entries on the stack are equal, and then op check sig basically checks whether the signature checks out. So, if you have the signature and if you have the public key, then if you apply op check sig, then it will verify that the signature is according to the is decipherable with the public key. That means it was created by the private key of the corresponding public key. So, these are called opcodes of the language. So, what we are seeing here is that there is a language, and this language is called the Bitcoin script language, and this language is very simple, and it has the semantics of this language is stack based, which means that we will assume that way the programs written in this language are executed is by reading one instruction, and then if the instruction is a data, then push it onto the stack. If it is a actual instruction opcode, then we take the things on top of the stack, maybe only the top entry or top 2 entry or top 3 entry depending on the instruction, and then we execute on that data that instruction, and then whatever is the result, we remove the entries on which you apply the instruction, and then you push the result on top of the stack if there is a result. So, that is how the semantics of this language works. So, it turns out that when we say script sig, that actually is a script, right. So, we would think that in the input transaction, so when I use a transaction as my input, so what I am doing is that I am looking at a previous transaction in which I was given some money, and I am going to sign that, saying that I am now signing to use that money. So, it is called redeeming the input transaction, the output of the previous transaction. So, to redeem I need to give a signature, but instead of a plain signature I give a script. Similarly, in the output I saw that I am supposed to only say whose account it should go to, but instead of giving just this account number as a hash of a public key, I have to write a script, and that is called the script pub key. So, we will see how this thing works, and then whoever is going to validate the transaction has to put script on top of this script. So, script is basically a set of instructions and data values, and this is also a set of instruction and data values. So, I concatenate them. So, I have first these instructions and then I have these instructions, I get a longer script, and then I have to execute that script and in a stack based system. And when I execute, if the execution goes through well, then it is all fine, the transaction validates. If the execution throws an error, that means something did not work out, that means either this script has a wrong information or this script has a wrong information, and therefore, the transaction is invalidated. So, that is the idea of this scripts. So, the goal of the Bitcoin scripting language is actually to have a simple compact way of validating the transactions, and we want to keep the machinery to validate the transactions very simple. That is why the language is also very simple. It has instructions to support cryptography. So, it has single instruction to compute a hash, it has single instruction to validate a signature. So, this is actually in that sense the instructions are pretty powerful, but it is stack based, and therefore, and every instruction is executed in just once, and therefore, the time and memory is basically linear in the size of the script, and therefore, it is pretty limited, because we do not want, see, these scripts are written by somebody else, right, because when you are validating a transaction, the transaction script seg or script pub key is written by the person who actually put the transaction in. Now, if he is a malicious user and he had a time consuming instruction there, then all the validators will actually be getting into a huge time consuming computation, and which will delay or validating all other transactions. So, we want the language such that it is not possible to get into an infinite loop or very expensive computation. So, this language has no loops in its structure, and therefore, it is not Turing complete. So, Turing complete languages, like all programming languages that we normally use, are called Turing complete languages. So, if you have taken a course in theory of computation, you probably know what that means, but Turing complete languages can design or can express very complex functions, whereas this kind of a very simple language with no looping cannot express any arbitrary functions, and therefore, and that is by design, so that the transaction validation cannot be attacked by a malicious user by putting in a transaction where he puts a script which goes into an infinite loop and things like that. And it is inspired by previously available language called Forth. We do not need to worry about that language, but we have to understand the very basics of this language. Now, why are we talking about this language? That when we come back, we will talk about that, and we will be actually discussing the concept of smart contracts in this context, and then you will understand why, even though we are not interested in cryptocurrency, we are talking about Bitcoin scripts. So, we will come back.